Okay, today we will continue the signal conditioning in the second part. So in the first part, it was really basically a review. So we saw how we use amplification through amplifiers, filtering, and we stressed on the low pass filter being active, and then we showed what is a passive low pass filter without going into its details. So in this part, we will start with the long list, if you recall, of sensors that have a change of resistance based on a change of measurand. So, for example, if you take the case of basically a potentiometer, then going into a strain gauge, resistance temperature dependent, RTDs, thermistors, LDRs for the light dependent resistance. So we have a huge list of sensors which output is based on a change of resistance when I have a change in the environmental measurand that they are measuring. So we know that this change of resistance cannot be read as is with any brain that we are using, being a microcontroller or a PLC. So we need to convert this delta R into a delta V. So this is what we will cover in this part. So we know a very basic conversion. So we'll cover two conversions, in fact, or two methods, the voltage divider and the Wheatstone bridge. The voltage divider, you know what is the voltage divider. A voltage divider is simply two resistances in series connected to a power supply, and then we will take our V out, which is the voltage drop across the second resistor. And since there is one current passing through R1 and R2 and doing some small mathematical manipulations, I will arrive to V out equals to R2 over R1 plus R2 times Vn. So now what I have is that this R2 resistance can be changed to be a sensor. So basically I will put a Vn, which is a constant DC power supply, which I know what is the value of Vn, and I will measure what is the value of V out. And as you know, V out from this equation will change basically following the change of R2. So if I want to get the formula, we will have R2 is equal to V out over Vn minus V out times R1. So I will measure V out at each instant. Vn and R1 are fixed, and I will get R2. So I will know exactly what is the change of resistance of this sensor. And from the calibration curve, I can know what is the temperature, what is the pressure, what is the light, or the displacement, what have you. Okay, so this is the case of the voltage divider. As you can see, it's a simple setup, simple calculations. The drawback of the voltage divider is twofold. One is that if you will do the relation between delta R and delta V, I did not put it here, but what you will do is consider that R2 will change. So I will have R2 star is equal to V out star over Vn minus V out star times R1. Now my delta R, which is R2 star minus R2, is equal to, you put this equation and you will have a nonlinear relation between delta R and delta V. Okay, because you will have your new V out in the denominator and your new V out in the numerator. So you will have a nonlinear relation. So this is the first drawback of voltage divider. The second drawback of voltage divider is that the system cannot be balanced for a specific output. Let me explain as much as I can this here, and maybe this will be understood more when I cover the Wheatstone bridge. But here in this case, and taking this equation of V out initially, you cannot have any value of R2 that gives me a V out equal to 0, unless I'm saying R2 is different than 0. So no value for R2 will give me a voltage equal to 0. So this is very obvious from this equation. Therefore, this is what I mean by balanced. So if I need a balanced system, so maybe I say that at a temperature of 23 or 25. This is what I need. I have a balanced system, so I neither want heating nor air conditioning of this room. Therefore, this cannot be done here. The V out cannot be equal to 0 for any value of R2. Okay, so these two drawbacks will be solved a little bit later when using the second method of converting delta R into delta V, which is called the Wheatstone bridge. So as its name, it's a resistance bridge, in fact. So it has 4 legs, and in each leg one resistance. So here we will have R1, R2, R3, and R4, and A and C nodes are connected to a power supply, which is Vs here. So let me just take the pointer. Okay, so here in this case, let's assume that, for instance, this bridge is balanced. So what is the bridge is balanced is when V out, which is the voltage difference between the points B and D, is equal to 0. When the V output is equal to 0, therefore, this voltage here is equal to the voltage at the node D. So in other terms, I1 R1 is equal to I2 R3, which is here. And so here what we do is we take, in fact, 2 KVL. So this is the first one, and this is the second one. So we take 2 KVLs, and we will solve these 2 KVLs by setting VB is equal to VD. Therefore, the voltage drop across R1 is equal to the voltage drop across R2, and the voltage drop across R3 is equal to R4, and I will have R1 over R2 equal to R3 over R4. So in this case here, what we have is that if for any instant I want my V output to be equal to 0, I have a condition that R1 over R2 should be equal to R3 over R4. If you compare to the voltage divider, this condition is different than having one of the resistances equal to 0, which is not a very practical case. So here we can have our output equal to 0 by setting this equation. Okay, so this is just one case. And what's the other case? The other case is when the bridge is not balanced, in fact. So when the bridge is not balanced, I want to see what is my V output. So V output is equal to VAB minus VAD. So it's voltage divider in the first loop is equal to Vs times R1 over R1 plus R2. And taking the second loop, VAD is the voltage drop across R3, which is equal to Vs times R3 over R3 plus R4. Do the subtraction of these two terms, and I will have V0 is equal to Vs into R1 over R1 plus R2 minus R3 over R3 plus R4. So now I have a relation of V output. Okay, where is the sensor? So in this case, one of the legs, one of the legs of the bridge can be, one of the resistances can be removed, and it can be replaced by a sensor. So in this case, I want, for example, I know that I have a resistance of 100 ohm when I have 25 degrees centigrade for this particular thermistor, for example. What I will do, I will put R2 equal to 100 ohm, R3 equal to 100 ohm, R4 equal to 100 ohm, and in this case, I have this equation that is verified, therefore my V out is equal to 0. So whenever my V out is equal to 0, I can ensure that R1 is equal to 100 ohm, so my temperature is equal to 25 degrees centigrade. Now, if this temperature changed, so I will have a new R1. So let us see what is the relation between this delta R1 and delta V output. So if I have any change, as I told you, from R1, so R1 plus a small delta R1, so it will give me a V0 plus delta V0. So my new voltage minus my old voltage, it will give me a delta V0. So it is equal to Vs into R1 plus delta R1 over R1 plus all of this minus R1 over R1 plus R2, and this is can be replaced by R3 over R3 plus R4 since this is balanced. In this case, so if you do the formula and you take V0 plus delta V0 and then you take V0, this term is constant in the two cases, so it will be removed and I will have here. So I will stop here and let us analyze this equation. So this equation is nonlinear from delta V0 to delta R1. However, what we can say is that delta R1 change can be very, very small compared to R1 and R2. So this term can be removed or can be neglected. Therefore, I will have a common denominator of R1 plus R2, and I will have R1 minus R1 removed. So I will have a linear relation between delta V0 and delta R1. So in this case, the first disadvantage of the voltage divider is solved in the Wheatstone bridge. Therefore, the change in voltage is linearly proportional with respect to the change in the resistance of the sensor. Pay attention, this jump from this equation to this equation cannot be made unless the condition delta R1 should be very, very small compared to R1 plus R2. If it is not very, very small compared to R1 plus R2, I keep this relation as my bridge relation, which will be a nonlinear relation, but I will be able to find delta V0 and delta R1 relation. Okay, so here there is an example where I told you that consider a RTD, which is a resistance temperature dependent, which has a resistance of at 0 degree of 100 ohm and forms one arm of the Wheatstone bridge. The bridge is balanced at the temperature of 0, with each of the other arms equal to 100 ohm. So the condition of R1 over R2 equal to R3 over R4 here is verified. So at the temperature of 0, I have V out equal to 0. This is what I mean by the bridge is balanced. The question is, what will be the output voltage from the bridge per degree change in temperature? So the RTD has a sensitivity of 0.0039 per degree Kelvin and Vs is equal to 6 volts, Vs of the bridge. So I need to see what is delta V0 per every degree change. So first I have to find what is delta R per degree change based off the formula of the RTD, and then using delta R inside the Wheatstone bridge equation to find the delta V output. So the RTD equation is given by RT minus R0 equal to R0 alpha T. So delta R here is equal to R0 alpha T. R0 is given, alpha sensitivity being given, so per degree change 1, delta R is 0.39 ohm per every degree Kelvin. Therefore, replacing delta R here and setting R1 equal to R2 and Vs equal to 6 as given, my output is 12 millivolt per degree. So now I have a relation that will give me the temperature change with respect to voltage change. So this is what I mean by conversion. So the sensor ideally and initially gave us a change of resistance based on a change of temperature. Okay. However, here through the Wheatstone bridge, I am having a change of voltage based on a change of temperature. So this change of voltage is easily connected to the microcontroller PLC, and then I can know from this sensitivity what is the temperature that is being measured with the RTD. Look at this, another example. So the question is, what is the purpose of the circuit? Okay, this is a typical question where we see a lot of devices, okay, of course, and you have to link all of them and to give me what's the purpose of the circuit. We see here a relay, so a relay which is very similar to the transistor. So I talked a lot about relay in class, but we did not arrive yet to a formal definition of the relay. But here what you have is that you may assume that you have here another circuit, okay, maybe with an AC power supply or and maybe with another device. And this relay, when there is current passing through this relay, this contact is closed and the circuit is closed and it can work. Okay, so let us get back to the basic question of on the slide is what is the purpose of the circuit? So let's divide the circuit into two or three parts. The first part is this part to the left of the slide. Okay, this part is in fact a Wheatstone bridge. Okay, so because we have plus V given, okay, and V out is taken through these two nodes. So this is a Wheatstone bridge, but repositioned in another way. Okay, this is a thermistor. So one of the legs of the Wheatstone bridge is a temperature sensor, which is in this case a thermistor. So, and here I have the second part is an operational amplifier, but without any feedback. So by looking at it, I can say that this is used as a comparator because there is no output feedback to the input. So this output here is either plus V or zero. So this transistor is either on or off. If it is on, there is current passing, the relay is energized, the switch is closed, and the other circuit will turn on. If this transistor is off, there is no current passing through the collector emitter, the relay is not energized, and this switch is still open, therefore the other circuit will not work. So the condition of the transistor off and on depends basically on the V out, which is here. So here we can set if, for example, I put here, I have to choose R2 by the way. Huh? So if R2 is chosen to correspond to a resistance, for example, of 20 degrees here. Okay, so when the resistance of the thermistor at 20 is equal to R2, I can say that the bridge is balanced because R thermistor over R2 is equal to R over R, which is case. Bridge is balanced. This is V out is zero, output is zero, transistor is off, relay is not energized. When the temperature is above 20, so I will have a delta R which is positive for this sensor. So I have a delta V0 which is positive. So I have a V out which is equal to plus 5, transistor on, relay is on, and circuit will go on because the switch will be closed. However, when the temperature is below 20, I have a delta R which is negative, delta V0 of the bridge is negative. Here it's either 0 or minus V set depending on the comparator. Transistor is off, relay is de-energized, and this will not work. Therefore, what's the purpose of the circuit? This circuit is used in order to turn on a device when the temperature of the thermistor is above a certain threshold, which is stated by the value of R2, which is here. So you can think about this as a heating system here, or an air conditioning or a refrigeration system here. When you have temperature above 20, the system will be automatically on. So you can see here that by using this bridge, this can be done through an Arduino. This can be done through a voltage divider. The output of the voltage divider or the Wheatstone bridge will be connected to the Arduino. The Arduino will test the V out, and then it will relay this decision to the circuit. But here it is done without any coding by a simple use of a comparator. In the next two slides, everything that I have explained here is explained more in details. Okay. So, however, all of this is already explained before. So the Wheatstone bridge also can be easily used for temperature compensation. We raised this issue before in class when we explained the sensors that are based on a temperature, on a resistance change, and I said that the problem with these sensors is that they can measure also temperature. So any change of temperature, so for example, if I'm using a strain gauge and I want to measure strain in any cantilever beam, if temperature on this cantilever beam increases, I am seeing a delta R which is positive, however there is no strain. So this is a problem in most resistances, sensors that are based on resistance change. So we said that, okay, we can use a temperature compensation dummy gauge, or what I call a passive. And I told you that, okay, I can use this strain gauge at the end of the cantilever beam, and I can put another similar strain gauge at the wall by ensuring that the wall has no strain. So whenever there is an increase of resistances of the two, I can ensure that this is coming from the temperature. If one strain gauge change, which is strain gauge on the cantilever beam, I can say that this is based on strain change, not a temperature change. But how can I connect this in real life on the bridge? So in fact, the bridge is really very easy to do a temperature compensation in it. What I will do is I will have one of the legs of the bridge, I will put it as an active gauge, and the other leg of the bridge, I will put it as a dummy gauge. So dummy gauge, to recall, this is the gauge that I put on the wall. So in this case, let's assume that for zero strain, V out is zero and this bridge is balanced. So whenever there is an increase in temperature, so when the bridge is balanced, R1 over R3 is equal to R2 over R4. Now, if there is any increase in temperature, R1 increase and R3 increase in the same way. Therefore, R1 over R3 ratio will stay equal to R2 over R4, and the V out will stay equal to zero. So as you can see, this compensation of temperature is done directly on the bridge. Whenever there is an increase in temperature, R1 and R3 will increase, and the ratio of R1 over R3 will stay equal to R2 over R4. We can use also more on this, and what we do is one strain gauge I put it in tension and the other one in compression. So in this way I can ensure that that these two cannot go in the same direction. The increase of resistance cannot go in the same direction unless there is an increase in temperature. So in this way, what I do is I put one leg is in tension, another leg in compression, and in tension. If there is an increase in temperature, all the resistances here will increase in the same way. Therefore, we will keep the same ratio R1 over R3 equal R2 over R4, and V out will stay equal to zero, even if there is an increase in temperature. So if I am in the control room and just checking my V output, I'm checking V output equal to zero. I don't even bother myself to see if there is a change in temperature, because all changes in temperature will be taken care by the setting of the bridge, and the voltage output of the bridge will stay equal to zero. This is one of the biggest advantages of the Wheatstone bridge, because it takes into it the temperature compensation by not only having one leg being the resistance, I can have another leg being a dummy gauge, or in other cases, one in tension, one in compression, and I can use the four legs of the Wheatstone bridge in this way. This can be useful for temperature compensation, and by using four of these gauges, the sensitivity of the bridge will be increased. Therefore, this, for a small strain, I am seeing a large delta V. Okay, by going back into the first slide of the first part of this signal conditioning lecture, now we can see that most of these signal conditioning were covered. We still have one, which is the IV converter. I will not stress on it a lot, but I have to cover this here because in order to be complete on the signal conditioning side, and in addition, this standard of IV, or what we will call the 420 standard, is largely used in most sensors in industry. Okay, so first, let's raise the problem in order to find the solution, as every time we do. So here the problem is that, okay, I'm using industrial sensors, and I am connecting these industrial sensors to one PLC, and this PLC, it is maybe in the control room, or in a place, in a location a little bit far from the machine or from where the sensors are. Therefore, I have a long connection wire. So here I have one disadvantage of these type of connections, especially when they are lengthy connections, is that I have addition of noise throughout this system. The next disadvantage is that even if I have good quality of wires, these wires, ideally, they are zero resistance, but in practice, they are not zero resistance. So when I have a very large length of these wires, I am having a resistance. Having a resistance, so I have a voltage drop. So the voltage that I will be reading from the PLC will be different from the voltage coming out from the sensor. This difference is due to the voltage drop across the lengthy wire. So this is the problem. What's the solution? The solution is not to transmit voltage. However, the solution is to transmit current. And this is the 420 milliamp standard. So it's called 420 standard, 420 transmitters, 420 receivers, but it's based on the 4 milliamp, 20 milliamp current. So in this way, what I have to do is that I have the current signal, as it's written here, can be sent without signal modification to a controller or a data acquisition system for further processing. So the first step, I have to convert the voltage at the output of the sensor into current, and the current will be transmitted through this long wire to the control room. Then I will convert this current into voltage, and this voltage will be read by the PLC. Okay, so this is a very important step to understand, is that we convert these voltages into current in order to transmit current, and then these current will be transformed into voltages in order to be read by the brain. The problem is that, okay, if my voltage is equal to zero at the sensor there, can I convert this to I equal to zero? Yes, it can be easily converted to I equal to zero. But the problem here is that, what's I equal to zero? I cannot read a zero current. This is one. Two, if there is for any condition where the wire is cut, so the current will be equal to 0 because the wire is cut, not because V equal to 0. So here there is a confusion on setting I equal to 0. So what we will do is that we will say that for any voltage equal to 0 in the sensor, I will convert it to a live 0, which I will set it equal to 4 milliampere. So now my 4 milliampere correspond to a voltage equal to 0. Now when I read a current equal to 0, I equal to 0, I will say that there's a faulty connection in my system. Okay, so this is why it's 4. And the full voltage, basically in industry we use 24 volt, correspond to 20 milliamp. So this from here it comes the name of the 420 standard. So 4 milliamp correspond to V equal to 0 and 20 milliamp correspond to the maximum voltage. The advantages is that transmitting signal as of current instead of voltage eliminate the effect of supply voltage variation, voltage drop in line resistance, and random noise induced in the loop. There are many types, and I will not go into these types. So this is a schematic. So this is my V in here. This is my sensor. I will convert my V into current through a VI converter, and this current will go into these lengthy wires. Okay, even if these wires contain a resistance, the current will stay the same, and then it will go into a IV characteristics. The easiest IV characteristic is a resistance. So whenever there is current passing through the resistance, I will measure a voltage. Okay, so the VI converter is not something very fancy, so it can be built as such. I will not go into details of here because we can get in IC, for example, AM422 as an integrated voltage current interface. By this, I arrive to the end of this part 2 of the signal conditioning.